Swayam Prabha. Digital India. Educated India.
In this lecture, let us continue with our discussions on high temperature gas dynamics. We will revisit the equation of state and continue with the discussion related to entropy of a gas mixture. In the previous lecture, we had discussed about the perfect gas equation of state, where we said that if we are dealing with a pure gas of volume V, of mass m, pressure P and temperature T, then we begin with the equation of state in this form, and then we can gradually move on to deriving different other forms of the equation of state. So, these are possible other forms, and then we moved on and we brought in the universal gas constant, and then we saw that universal gas constant can be giving rise to some other forms of the equation of state, like the ones we see over here, where instead of the specific gas constant we have the universal gas constant coming in. And this needs to be very importantly noted that wherever we see the specific gas constant, we are basically talking about the equation of state written per unit mass basis, while the universal gas constant, its presence means that we are talking about per mole basis. We introduce certain other nomenclature. For example, we introduce the concept of concentration of moles per unit volume. We introduced molar volume. We introduced the concept of number of moles of the gas based on the molecular weight and the mass of the gas, and so on. Additionally, we introduced the number of gas particles, and then when we move on to the next slide, one of the things that happens over here is that introduction of the Boltzmann constant, which is the gas constant per particle. This is one form which we are interested in on a per mole basis, where the mole mass ratio is introduced, the eta, which gives another possible form of the equation of state on a per mole basis. And then when you go to the per particle basis, then you see the presence of the Boltzmann constant in these forms of the equation of state. Therefore, we came up with a lot of forms, and then we consolidated all that into a simple tabular form here, which would be easy for you to recall on mass basis, mole basis and particle basis respectively, so that you can easily move from one form to the other. And this is as far as a pure gas is concerned. When we try to move on and look at a gas mixture, then there would be numerous species present in the gas mixture, and that is where we have to look at each one of the species in particular, as well as their collective effect in the mixture of the gases. So, we start with the forms which are relevant for a pure gas, which are written on the left hand side of these boxes, while the ones on the right hand side, here, here as well as here, those are the forms pertinent to the gas mixture, and they have been written for each individual species. So, when we put a subscript I, it basically means a certain species. So, all these equations have to be extended to all possible species that are present in the mixture individually. And per unit mass basis, these are the forms per mole basis these are the ones, per particle basis the rest. And then there are important relations to be kept in mind as far as the collective effect of the species are concerned. For example, each one of the species they contribute to a certain amount of partial pressure, and collectively they give rise to the total pressure of the gas mixture. There is this very important law, the Dalton's law of partial pressures, which basically states that the summation of all partial pressures would give rise to the total pressure. And then there is another important expression here, that of mass fraction, which are nothing but summation of the density ratios of each one of the species scaled with the density of the mixture. So, this is basically the mixture density. Let us look at some more interesting and important relations which connect the species parameters with that of the mixture. So, here is Dalton's law once again. There are other relations here which are also important for us to know. So, the one here gives rise to the definition of mole fraction. So, when you take a ratio between the partial pressure of a certain species with respect to the mixture pressure, then that ratio basically gives rise to what is called as the mole fraction. And basically you are looking at the number of moles of that species scaled with the number of moles present in the mixture. When it comes to mass fraction, it is the density ratio, and the important relations to watch for are what happens when we take a summation of the small c I and the cap x I. They both go to unity. Then comes calculating the specific gas constant in terms of the specific gas constants of the individual species, and what you see is that they have to be weighted based on the mass fraction. Similarly, the specific volume for each species can be worked out. Then comes calculating the molecular weight of the mixture, and there are two alternative forms written over here in terms of the mass fraction and the individual molecular weights of species, as well as the mole fraction and the individual molecular weights of the different species. So, we have to be comfortable with the equations of state for perfect gases to begin with for a pure gas, and then trying to extend it to a gas mixture, because very often when we deal with high temperature gas dynamics, we are going to deal with air as the medium, and air comprises of different pure gases. It is a mixture of pure gases. Under normal temperatures and pressures, they are non-reacting, while when we look at elevated temperatures, which are very often going to occur in high speed flows, there they start reacting. Different kinds of chemical reactions lead to the mixture composition change and so on, and therefore, we have to be very comfortable handling the perfect gas equations of state for both pure gas as well as mixtures. We take one step ahead towards looking at the thermodynamics and chemistry of gas mixtures. So, we start with an equation for entropy. We would try to derive it in terms of a reference thermodynamic state, and to begin with we visit a familiar equation, the entropy change between two states 1 and 2 for a calorically perfect gas, which we have looked at earlier. We are just revisiting the equation. So, if we say that the state 1 be referred as a reference state indicated by the nomenclature T ref, P ref and S ref respectively for temperature, pressure and entropy, and then we refer the state 2 without the subscript 2, then the equation on top basically takes a form of this kind. Let us derive an expression for the entropy for an equilibrium chemically reacting gas mixture. This could be air, for example. reacting air, but under equilibrium conditions. That is a very important constraint that we are imposing, and we will gradually understand what is the implication of that constraint. Now, in the following equations, we are going to follow a certain nomenclature. We are going to use uppercase letters which would indicate quantities per mole. So, we are going to look at the equations on a per mole basis. Here we once again recall mole fraction, which we were looking at a few slides back, and we remember that Ni is the number of moles of species I in the gas mixture, N is the total number of moles in the mixture due to all the species. And if we talk about entropy on a per mole basis, then entropy would come from different species. Each one of those species would have a certain entropy level Si, and weighted by the mole fraction, we will get the total entropy per mole of the mixture. Now, Si is the entropy of a particular species per mole of the species itself. Keep that distinction in mind. And then we would certainly need to work out an expression for Si, which we would like to substitute in this equation that we have written, which would give us the mixture entropy. So, in order to reach the mixture entropy value, we need to look at a detailed expression for Si. So, that is basically the target. Setting that target, we try to take it forward. Let us assume that the thermodynamic system comprises of only the pure species I. So, instead of having numerous species in the mixture, we just reduce it to a single one. So, there is only one pure species which now forms the thermodynamic system, and also let us assume that 1 mole of that species is existing at a temperature T and pressure Pi within the system. So, in that case, the first law of thermodynamics, when we apply it to this system, would give rise to a form like this. Since we are writing on a per mole basis, we are using the uppercase nomenclature here, and if there is a reversible heat transfer working here, from second law of thermodynamics, we should be able to write an expression for that del Q for a reversible case, which comes out to be this. So, that basically means the entropy change due to irreversibilities are eliminated here, and when we try to substitute that over here in the previous equation, we end up getting a form like this. So, we have basically combined the previous two equations to a form like this, and we recall the equation of state for species I, which would be represented in this form, which we have mentioned over here. And universal gas constant, of course, is involved here because we are talking about per mole basis calculations. And now, if you try to combine these two equations together, what you end up getting is an equation for dSi of this form, where the V by T ratio has Vi by T ratio has been replaced by the script R or the italic R by Pi, which means now we are kind of ready to integrate this. And if we want to express the enthalpy in terms of temperature, then we have to be a little careful about the behavior of the gas, whether it is going to be a calorically perfect one or a thermally perfect one. And since we are going to talk about a reacting gas mixture, and as we said earlier that if it is air, it takes rather high temperatures for the air to start reacting, and therefore, in all possibility, the species that we are looking at, the pure gas species I that we are looking at, may start behaving in a thermally perfect manner and not the calorically perfect one, which we generally see at the relatively lower temperatures, the normal temperatures that we see. So, Thermally perfect means the Cp that will be involved in the calculations will no longer be a constant, unlike calorically perfect gas, and would be a function of temperature. And therefore, when we try to replace the enthalpy here, it is replaced using Cp, which is a function of T and also the temperature. So, keeping these things in mind, we write down the dHi in this form, where we continue to recall that this is basically a function of T. And once it is all plugged into the equation for dSi, we have this. Let us try to integrate this equation starting from our reference state. So, the reference state entropy level will be given by Si ref, and to a final state where the entropy is Si. So, this is the final state to which it moves, and correspondingly we are moving from T ref and P ref to T and Pi as far as temperature and pressure is concerned. So, the limits are imposed over here in the equation for dSi, and once you integrate, what you get from the left hand side is basically the difference between these two entropy levels, and what you have on the right hand side is it will be easy for you to integrate this one, and you see that it is going to be natural log Pi by P ref. While here, in order to integrate this part, you need to have the temperature variation of Cpi to be functionally substituted over there on this particular integral, so that you can work it out. Now, if we imagine that there are a number of pure species comprising the mixture, then there would be a sum total effect of those several species, and if we have I number of them, then finally the entropy will be a sum total effect of all the entropy values. And now we substitute the expression for Si that we have worked out and shown in the previous slide into the summation that we have evolved over here. We have therefore found a way to obtain an expression for entropy of a chemically reacting mixture, and in order to find similar expressions for enthalpy or internal energy, if we feel that we can take a very similar approach like what we took for entropy, it generally meets with some difficulties, and therefore, for a chemically reacting mixture, when we try to work out enthalpy, internal energy and other thermodynamic parameters, we would generally need to go beyond the principles we are working with over here and have to look at tools of statistical thermodynamics or microscopic thermodynamics. We will try to spend a little time on that in the subsequent week, where we try to investigate the fundamentals of that area. Now, we have the summation over here, where we have substituted the form that we derived in the previous slide. You have to recall this form that we have derived here. So, that basically gives us this expression. Remember that there was a Si ref on the left hand side of the equation, which has now moved on to the right hand side and weighted by Xi. Similarly, this is the portion which comes from the integral involving temperature and pressure respectively, and that gives the entropy per mole of mixture for an equilibrium chemically reacting gas mixture. Now, in the above equation, S ref is the reference entropy level for the gas mixture, that is where from we started, and if you recall that we reached the final value, which is Si, and each one of the species in the mixture would reach those final values, and correspondingly the mixture entropy level would be decided. Now, the S is basically a function of which all parameters. If we look at it carefully, it is definitely dependent on temperature. T, it is basically the final temperature that the mixture reaches, and then it is also dependent on the individual partial pressures of the different species present in the mixture. And we recall that the individual partial pressures are also functionally dependent on the temperature as well as the pressure of the mixture, which basically means that the entropy of the mixture is dependent on the temperature as well as the pressure of the mixture. Now, therefore, we finally are able to show that the entropy is dependent on temperature as well as pressure of the mixture. When we use the above equation for entropy between two states, then we get the entropy change, and this of course is in terms of the mixture. We are not looking at the individual species contribution over here, but we are interested to find how the functional dependencies are established through this equation. So, we are basically moving from an initial temperature T I to a final one T 1 to a final one T 2, an initial pressure P 1 to a final one P 2, and then correspondingly you should be able to get two different levels of entropy corresponding to the T and P values, which are associated with the initial and the final states. So, having said that, we move on to another concept. We recall the expression which we have discussed earlier in the context of second law of thermodynamics, that the change in entropy, say the differential change in entropy, one part of it basically comes from the del Q by T contribution, the other part comes from the different sources of irreversibility, and we already know that there are sources related to the sources of irreversibilities in a thermodynamic system. It is caused due to finite gradients, and different effects like viscosity, thermal conductivity, mass diffusion, etc., can bring in these irreversibilities into the flow field. Additionally, irreversibilities can also be caused and accounted through chemical non-equilibrium. So, for a specific process connecting the two states 1 and 2 mentioned above, it is important for us to know how much of the entropy change is actually caused due to irreversibility. So, the change that we are talking about over here, we are not able to exactly identify how much of it came from the irreversibilities. Now, from high temperature gas dynamics point of view, we are mainly concerned about how far the nature of the chemical reactions which are occurring contribute to these irreversibilities, and therefore, in particular we are interested to know the irreversibility contribution which is coming from chemical non-equilibrium. So, though we have stated earlier that here we are talking about performing these calculations by assuming equilibrium, but we are also interested to raise this question that, well, if chemical equilibrium was lacking in the system, in a non-equilibrium situation, how much of the entropy contribution would be there from the non-equilibrium part of the reactions. So, let us try to conclude. We discussed about different forms of the equation of state for a pure gas as well as a gas mixture comprising of different species. We started discussing about an expression for entropy of a gas mixture, and we will try to take the discussions forward in the subsequent lecture, where we talk about the concept of Gibbs free energy. Thank you.